maybe it's too long. So I just changed the length of the page, but probably it's too much. Let's see.
Try page setup.
Yeah. Is what I did, but it was kind of okay. Probably should work now. Okay, so this is our data, and another piece of data is the dimension vector E, which is also an element from the same set with the extra condition that EI has to be no larger than DI. And then we put forward the following definition, saying that the Grassmannian of E-dimensional subrepresentations of M is just the set of subrepresentations in M, such that N is Q submodule, and dimension of N is E. So this is the definition. Why it's natural? Because, say, example, so if Q is just a one quiver, one vertex, no edges, no arrows, then M is just a vector space, say, just M. And then GUR E of M is just the usual Grassmannian. Well, however, in general, there are much more complicated and much more interesting examples. So another example, say, let Q be, say, A2 Quiver, and let's take a very simple representation, M just K to the D to K to the D and the identity map. And then, well, we have to take E to be E1, E2. And there are two separate cases. So first, if E1 is greater than E2, larger than E2, what's that? So then what is the corresponding Quiver Grassmannian?
Zero.
Right. This guy is just 0. And if E1 is less than or equal to E2, so then what is GUR EM? So how to describe it? So we have very simple representation.
It's a partial set, right?
Absolutely, yeah. So this is just flag of E1, E2 inside the D-dimensional vector space. Alex, Andrei, is it clear, or we better discuss it more details?
Yeah, so M is fixed, right? And then the dimension of E2 should be less than the dimension of M less than D, right? Or,
Yeah, so we agreed from the very beginning that we have
Ah.
the condition that EI is less or equal than DI. So this is okay. So this is a nice smooth variety, and well, here we don't have any other options, but in general, well, things might be much more complicated. Let's work out another example. So still Q is still A2, but let's use a bit more complicated representation M, which is map from one two-dimensional space to another, but here this is rank 1 map with one-dimensional kernel. And let's put E to be just 1, 1. And then let us ask, what is the Grassmannian E of M? So can you tell me?
is it two lines that intersect in a point, or?
All right, right, absolutely. Andrei, is it clear why this is true?
No.
So let's then work it out. So Alex, can you maybe give some details why?
So we can identify, like we can take the the idea is that the left-hand side and the right-hand side each correspond to the lines, and then they intersect if the point on the right, like in K2, and the
Okay.
rightmost,
You're
if
right.
the
You're right. Let's do it very explicitly. So I mean, by the very definition, this guy sits in P1 times P1. Yes, because so after all, each point of the Grassmannian is a pair of two one-dimensional subspaces inside the corresponding two-dimensional spaces, right? So let's assume that we have coordinates in these P1s, and these coordinates are, say, x1, y1, and x2, y2. And also let us assume that our map here from K2 to K2, so our rank 1 map, sends pair xy is sent to x0. Okay, since this is rank 1 map, it just means that the one vector is sent to itself and another vector, for example, to 0. So then let me denote it by phi. So what do we need? We take a line x1, y1, and then we want this line to be so we take a line. Let's just take a vector x1, y1, and then it is mapped to x1, 0. And this vector has to be contained in a line passing through x2, y2, right? So what does it mean? So when this guy sits in k x2, y2, so what is the condition on x1, x2, and y2?
Y2 should be 0.
No,
And x1 should
not necessarily. So, I mean, if y2 is 0, then it works, but what is the general condition? So I claim that y2 might not be 0, but this vector still might belong to the line.
x1 multiplied by y2 should be 0.
Absolutely. It's equivalent to saying that x, y, 1, 2 is 0. Okay, so we look at the pairs of points in P1 times P1, which are x1, y1, x2, y2, such that x, y, 1, 2, y2 is 0, right? But this is equivalent to saying that either x1 is 0 or y2 is 0. Yes, in the first case, x1 is 0 means that we have a P1, which is somehow so we are interested in, so in the first case, this is 0, 1 times P1, and then we take the union of P1 times 1, 0. Okay, and these are two P1s and they intersect in one point. And this is exactly the picture which Alex explained us. Okay, so you can see that the variety is neither reducible nor smooth, so it's kind of something. And let us consider even more kind of odd example. So let's consider Q to be a two-Kronecker quiver.
The Nakajima Quiver varieties, are they always smooth?
No, no, no. But they're very different. Okay, and so two Kronecker quiver, so meaning that we have two vertices and two arrows. And let's take M to be just a representation of dimension 2, 2, and the upstairs map, the identity map, and the downstairs map is something like 1, 2. Okay, so just diagonal matrix with 1 and 2 on the diagonal. And let us take E to be E1, E2, which is just 1, 1. So can you tell me what is Grassmannian E of M?
Two points.
Right. So these are just 2 points because you see the upstairs map is the identity map. Therefore, the two spaces on the left and on the right, they have to coincide. However, they also have to be mapped one to another by this matrix. So therefore, we're just looking at eigenvectors of the downstairs matrix. And it has 2, and these are 2 points we are interested in. Okay, so this means that the Quiver Grassmannian here is even not connected, right? So it means that so there's no point to consider all possible Quiver Grassmannians. So they are very different, and they do depend on the representation, on the dimension vector, on the quiver itself. So well, you can get whatever you want. However, let us do several. So I mean, let us try to understand why this construction is natural and how it can be used and what's the point. So maybe one couple of remarks first of all. So the first remark is that so the Grassmannian, you remember the usual Grassmannian. gur E of M can be realized as the quotient of the forms from Ke to M. Modulo GLE. Well, however, these should be embeddings. So I didn't say anything serious, just saying that well, you have your Grassmannian is the variety of subspaces in a given space, and then you just consider all possible embeddings of this e-dimensional space inside M, and then you don't care about bases, you just quotient down by GLE. So well, should be an analog and now analogous construction is available for all Quiver Grassmannians. And it's the first remark, so I hope we'll get there and we'll discuss the details, but at least so let me mention from the very beginning that such a construction does exist. And another remark is that so suppose we consider this Grassmannian EM, and we consider the tangent space at some point n to this Grassmannian. So do you remember how to describe this tangent space?
As come from the quotient of the, so maybe it would be a quotient of M by N to
But
M.
well, I mean, this is not cotangent space.
That's
but
the cotangent space.
So
Yeah. So
what you are saying is a cotangent space, and how
Yeah.
does the tangent space?
So come from N to M quotient N.
And these are just Hom spaces over K, yes, just linear maps. And so again, similar formula. Does exist in the general setup. Okay, so these are two remarks, and now let us somehow discuss a construction which makes the use of the Quiver Grassmannians very, very important. So this is called the universal Quiver Grassmannian. So in short, the idea is to consider family Quiver Grassmannians, the family E of M with different Q modules. So in other words, we can change M, and then as we saw already in the examples above, the varieties do change. And here somehow an interesting thing is what's happening when M becomes different. So you see the as I said, Quiver Grassmannians, they are kind of a model. They can be considered as a model for describing some nice varieties, and then you somehow change the representations, and the varieties got deformed. And this is the way how you can degenerate or deform your variety depending on what you want. So construct a family of varieties, which is somehow useful in many situations. So what's the definition? So first of all, let us introduce the following notation. So we take our E and our D with the usual condition that EI is less than or equal to EI. And then we consider GR E D. It's just a product of Grassmannian's EI. Okay. So just like the product of classical Grassmann varieties. And also recall the notation for the rep QT. So this is the space of representations of D-dimensional representations of. Okay, so now we are ready to define our main object. So the universal Quiver Grassmannian so let's denote it by GR Q E D. So as you can see, it depends on two dimension vectors, E and D. And so upstairs we have the Q, which makes it different from just the Grassmannian ED. And actually it sits inside the product of Grassmannian and rep QD. Okay. And so by definition, this is the variety of collections of, say, well, let me put it, Ni. These are just sub representations, oh, sorry, subspaces inside K to Di, I over Q naught. So these are just points in the Grassmannians. And here we have collections of maps phi alpha from, maybe I shift it a bit. So phi alpha from K to G start of alpha to K of G terminal of alpha, such that, so overall alpha Q1, such that phi alpha of N start of alpha sits inside N terminal. So this is just actually a fancy way of saying that we vary our representation and we consider sub representations. I'm sorry, I should have said that the dimension of E and I is E. Okay, so this is the definition. Now let's look, let's understand what is this guy, how does it look like. So first of all, we have the maps, just the projection maps from the Grassmannian to the product of Grassmann varieties. And also to the representation space rep Q D. And let us state first lemma. Well, it's not actually the lemma, it's the observation. So if we take M a point in rep Q of D, then what is Q inverse of M? So can you tell me? So we take a, yeah?
Sub-representations of given dimension. Or
Yes, but we have a name for it already.
Grassmannian
I guess this is
Just a Quiver Grassmannian, right?
Yeah.
Just by definition, this is just Gur E. Yeah, so I just saying that well, this Q somehow produces, so therefore U is a map from our universal Quiver Grassmannian to an affine space. Yes, because you remember this representation space is very simple. It's just the sum of home spaces. Yeah, so it's just an affine space. And with fibers being Quiver Grassmannians, so this is what I just said at the very beginning. And now bit more delicate question is description of P. So so I claim that the map P is a vector bundle over the product of Grassmann varieties. So can you explain why? So, well, I want to ask you why this is a bundle, vector bundle, and what is the dimension of the fiber? So maybe the first thing to say is what is, suppose we are given, so suppose we are given a point. So Ni inside K to Di in Gur E D. So what is the inverse of this point? So how to describe it?
these are like sets of maps which map to say an S of alpha to an T of alpha. So yes, so but that's right. So but these are maps from where to there to where?
Maybe Ni to the quotient.
I mean, well, that is right. So this is the collections of maps com m k s of alpha k d of alpha overall alpha such that phi alpha and s alpha sits in n t alpha. Okay, so what is this space? So I mean, so how to describe it?
So it looks similar to representation space of dimension indexed by dimensions of n.
Yes, it looks like, but you see
It contains it, but
Yeah.
not.
Not
equal.
exactly, yeah, because the difference is that those phi alphas, they are maps from a larger space to oops, what did I write actually? You didn't correct me, but here this is some nonsense, right? So here it should be ds of alpha and gt of alpha, right? So this phi alpha are maps from d-dimensional space to another d-dimensional space, right? And then with this extra condition. So how to
So
describe?
it's like block triangular matrices, right?
So can you elaborate on this? So what are the blocks? So how to draw them?
Okay, left upper is mapped from n s of alpha to n t of alpha.
Okay, so here we have
Yes, in the left upper we have something in left lower, and
so you are muted.
sorry, okay, here is 0,
Okay.
and in yes.
Okay, so in particular, we can see that, so this is exactly phi inverse of ni. And in particular, we see that actually this is the vector space. Yes. So then this is isomorphic just to affine space. And what's the dimension of this affine space? So
Okay, we should sum over all edges,
okay.
and the first term, I mean, we have two terms in each summed. The first is to say nt of alpha, dimension of nt of alpha
This is E, yes, in our
multiplied
notation, yes?
by
Just E. Yes?
oh, okay, yes, e s of alpha. Okay, we multiply it by e t of alpha. Then we have, okay, to say e s of alpha, but multiply by d t of alpha. Oh, we can have bracket and okay.
So you are saying that here we have d t of alpha times the difference, yeah?
Oh, sorry. No. No, it's yes, it's dt of alpha, and we multiplied by d s of alpha minus e s of alpha. Sorry.
Right.
Yes.
Right. That's true. Okay, so another way to write it is that this is just a to sum over alpha ds of alpha gt of alpha minus es of alpha gt of alpha minus et of alpha. Yeah, so Andrei suggested to just write it as a sum of two things, the upper left block and the right block. And another way is to write as a difference of the whole matrix and the lower left block. Okay, so what is the conclusion? So the first conclusion is that the Grassmannian E D U is smooth and irreducible. Because I mean this is a vibration over the product of Grassmannians, just the fiber being a vector space. And the second thing is, what is the dimension of the universal Quiver Grassmannian? Can you tell me? So how to compute the dimension of this variety?
We can take sum of dimension of fiber and the dimension of base.
Absolutely. So what's the dimension of the base?
It's sum of dimensions in each point, like EI DI minus EI.
Absolutely. Over I from Q0. And then plus some ds alpha dt alpha minus eds alpha dt alpha minus et. Okay.
Sorry, but how can we conclude that it is irreducible?
Because you see, we have a vibration over a smooth, irreducible variety. So I mean the base, just the product of Grassmannians, right? And therefore, so if you have such a vibration, it never can be reducible, because I mean, if you have two components, then the projections would give you the components of the base. Okay, so in general, if you have a vibration over an irreducible variety, then it's irreducible. Okay.
But okay.
Good. So now let's look at, so let's at the second projection. So I mean the projection of EQD to the rep.
Sorry.
Yeah.
Can I ask?
Absolutely.
But well, we can have like two components, right? But we can have component which is like proper in the whole bundle, but not proper in on like projection of it. It's whole base, but it's not. But the component does not coincide with how to say with the bundle with
Well,
the total.
But you see, if you have an irreducible component, let us consider the projection of this component to the base. Okay. So I claim that the component contains, so if it contains some point, then it contains the whole fiber. So I mean, if you have a point in an irreducible component, so you consider projection downstairs, and then you consider the whole fiber over this point, and then an irreducible component has to contain this fiber. And the reason is that the fiber is just an affine space. And if you have two irreducible components, say, then this affine space should be cut into two. Well, I mean, this affine space would also become reducible, which is no way. Okay.
Okay, I see some arguments.
So therefore,
okay.
each irreducible component is a union of some fibers. So therefore, just
Yeah, then it's true. But okay.
good. So let's look at the second projection and let us compute. So the observation. Let us compute the difference between dimension of EQ minus dimension of rep QD. So can you tell me what is this difference? So we have the formulas for both things.
Sorry, in representations we don't have quotient by GLE or we have.
No. We don't. This is just an affine space.
Then
Just direct sum of spaces.
Then this dimension is just sum over edges, like dt of alpha, ds of alpha, and this will cancel one term in dimension of universal Grassmannian.
So that's true. This is the term, right?
Yes.
So the conclusion is then so this is the sum over I, EI, GI minus EI, minus the sum over alpha. This is the term which is left here, yes? E S of alpha, GT of alpha, minus ET of alpha. So do you remember, have you seen this thing before? So do we have a name for this?
What's the value of the Euler form on the vectors EI and GI minus EI?
Right. Well, so this is so this means that, let us put the following corollary, that the dimension of Quiver Grassmannian E M is greater than or equal to E G minus E for any M such that the dimension of M is D. Okay. So can you say a few words why? And actually this, so okay, so let's start discussing.
We obtained that the fiber of the first, no, of Q is Grassmannian of M, and that the observation is calculation of dimension of fiber.
Right. So indeed, you are right. So what do we know? That we have this affine space downstairs. And upstairs we have our big thing, which is the universal Quiver Grassmannian. And the fibers are the Quiver Grassmannians, just the Quiver Grassmannians. And so the claim is that we know that the difference of the dimensions between the total space and the base is E d minus E, the value of the Euler form. However, we don't know, and this is not true, that this map is a fibration. So it's not. Actually, we'll work out an example just in a minute. But what I want to say that the fibers may be different, and they are different. And in principle, they are of different dimensions. But this is a map between one smooth irreducible variety to an affine space. And then the claim is that the general fiber is of the expected dimension, and the fibers in some special points may have a larger dimension. So this is what is called sometimes in algebraic geometry the semi-continuity theorem, that the special fibers have larger dimension than a general fiber. So let me just write. So the general fiber has an expected dimension E, the value of the Euler form, and the dimensions of special fibers may be larger. So, let's work out an example. So an example is as follows: Q is A2. T is 2, 2. E is 1, 1. So let's write down all the gadgets we have here. So we have this Grassmannian D U E, the universal Quiver Grassmannian, and then it projects onto the Grassmannian DE. So sorry, just 1 minute. Hello. Okay, so this is the oops, but sorry, I misplaced the coefficients here. So it's E and D, right? And this is how I wrote it, right? So the downstairs was E, right? Correct? So first of all, what's that?
P1 and P1.
The product, yes? Of two
Yes,
P1s.
product.
Okay. And here we have rep QG. So what is that?
Four-dimensional affine space.
Yes, just home from K2 to K2, right? So just after all, just a set of all matrices A, B, C. Okay. And so this means that this guy sits in P1 times P1 times A, B, C, D. Just K4. And okay, let's do one more thing. What is the fiber here? So what's the dimension of the fiber here?
I think it's 1.
No. Why one?
I tried to calculate. Sorry, it's difference. Okay.
What did you
Alex,
say?
say it
What did
again.
What did you say? 2?
Sorry. So what is the fiber?
I thought it was
A3.
3 because it's the condition that the first one is mapped to the second.
Yes. So what is the fiber?
At A3.
Yes. Yes. That's right. Andrei, do you agree?
Yes, yes.
So in particular, this means that the dimension of GR E QD is what?
5.
Yes, 5. And one more thing, what is the value of the Euler form on ED minus E?
This is 1.
That's right.
Sorry.
Why?
Why it's 1?
I think
Because this is E1 times G1 minus E1, so 1 times 1 plus 1 times 1. I write it explicitly. And then minus 1 times, because we have 1 arrow. So this 1, and you see this agrees with the thing with that 5-dimensional universal Quiver Grassmannian is mapped by Q to a 4-dimensional vector space, affine space. And then this 5 minus 4 is exactly our 1. Now let's consider this projection map. GR GR E QD to A4 A, B, C. And let us describe what is P inverse of a point ABCD. Can you tell me how does it look like?
Can we assume that the matrix is degenerate first?
Well, I mean, we have to work out all the cases, yes, because we are interested in the fibers for all points in this A4. So
it's the a subset of P1 times P1 where the first thing is mapped to the second one. So
yes.
if it's not degenerate, I suppose the fiber is just P1.
Absolutely. So this is P1 if AD minus BC is not zero, right? Okay. Now assume that it is degenerate.
It still depends, because if all of them are zero, then it's just P1 times P1. But if it just has rank 1, then
Yes. And so yes. So let me. Yes, and otherwise, what is it? So if it's non-zero but degenerate.
So it's P1 veg P1.
Yes, we just saw this example, yes. So this rank 1 map, yes. Otherwise. Okay. So does it make sense?
Why is this P1 if it's non-degenerate?
Because if it is non-degenerate, then this map has no kernel, right? I mean the ABCD, and therefore, so what? As we decided, P inverse of a matrix is just a pair of two one-dimensional subspaces, one in the first two-dimensional space, another in the second. One is mapped to another, but the space has no kernel. Oh, the map has no kernel. Therefore, if you fix the first space, the first one-dimensional space, then the second is completely fixed.
Ah, okay, yes.
Okay, so let us draw the picture. So the picture is as follows. So you have this A4. And here you have a large universal Quiver Grassmannian. Then over a point 0, you have a two-dimensional thing, which is just P1 times P1. So you see it's of dimension 2. Now we have one hyper surface well, cut out by the conditional determinant is 0. Yes, it's 3-dimensional. So this determinant is 0. And over this thing, so this over 0, and over this thing, this is these are two P1s meeting at one point, right? So this is one-dimensional, and over all other points, it's just P1.
is this a conic bundle, or
Say it again.
is this a conic bundle, or
But what do you mean by a conic bundle?
that it's a conic outside of somewhere where it's degenerate over? some
But-
closed subset, and then it's like a degenerate conic, two lines intersecting each other.
Yeah, but you see, in this special 0 point, it's even 2-dimensional, right? So the expected dimension is 1. So this is not a bundle, yeah. So this is not a fibration. So the dimension jumps at this special point. So and the fibers are different at non-degenerate point, at the degenerate points, and at 0. So this is some very concrete example when you degenerate UP1, and then this degeneration somehow preserve the dimension until you get to this very special point 0. And then the dimension jumps and becomes 2. So you see the dimensions, this is a 5-dimensional variety. 5D variety. Smooth and very nice. But when you project it onto A4, the fibers are different and not of the same dimension. Okay. This is the picture. Good. So now, yes. So let me state one proposition, which is of the general nature. So it's natural to ask, when can we say that the dimension of the Quiver Grassmannian is indeed the one we expect? And the answer is as follows. So assume that M is rigid. So it means that the X of M is 0. Then the dimension of any Quiver Grassmannian is indeed the one given by the Euler form. Can you explain why? What is so special about rigid representations? So what is the so M? So if M is considered as a point in rep QD, so what is so special about the rigid representations?
It's how to say, co-dimension of orbit is 0, and then we have only one orbit because it's like at most one orbit of this.
0.
So as far as I remember, then we have only one representation.
Yeah. So, but then we can so we conclude that dimension of the fiber of P over M is of expected damage, is the expected one. Yes, because this is the general point in the base space, therefore the dimension over this point is the one we somehow think of. Okay. This is it, but in general, let me repeat that the dimension may be large. So what else?
Can I ask a question?
Yeah.
So is it trivial that if we consider a set of points in our representation space that has with the same dimension of fiber over P, so that set is exactly the orbit.
No, and actually, you see, we see this in this example. Yes, so we know that the dimension of the fiber over the degenerate matrices, some of them non-zero, is still 1. Yes, but the orbit of a non-degenerate matrix is, well, these are non-degenerate matrices. Yeah, so you don't get there. So you may have still the expected dimension, but for different orbits.
So so the orbits are the sets with the same dimension of fiber.
No, what is true that if you take 2 different points in the same orbit, then the fibers have the same dimension.
And vice versa.
Vice versa is not true, because you see, this is the example. So if you consider 2 matrices, let's consider one matrix which is just the identity matrix,
Okay.
and another matrix of rank 1.
Okay.
They're not in the same orbit. Do you agree?
Yes.
But the fibers over
Oh, okay. Okay. But
have the same dimension.
is it true that they have isomorphic?
So I mean, if you change the orbit, then the Quiver-Grassmannians are not isomorphic. No, I think in general this is also not true. I can't give you an immediate example, but I think there might be 2 non-isomorphic representations such that the corresponding Quiver-Grassmannians are isomorphic.
Okay.
So I can, well, I think there are idiotic examples, like if you take the dimension vector of a subrepresentation larger than the dimension vector of representation itself, then both are going to be empty, but this is kind of not the good example. But I'm sure that you can give more kind of
Okay. Thank you.
normal. You're welcome. Okay, so and maybe me also write that the same reason for rigid representations, the varieties GUR EM are smooth and irreducible. Okay, so now let me give you 2 more, let me say maybe 2 more things. So the first thing is as follows. So recall the formula T and GUR E M is isomorphic to home space over K and 1. Okay, so we state the following position, saying that the let N be an e-dimensional U submodule of Q module. So then T n of GUR EM is still isomorphic to the home space, But now this is Q homomorphisms. So the maps which are kind of just not all the linear maps, but compatible with the actions of operators on Q. And here still n mod n. So well, for example, let us maybe do one example here. So suppose we have our favorite A2 and D is 2, 2 and E is 1, 1. So let us work out the case. So assume that M is a map from K2 to K2, phi, and the rank of phi is 1. Okay, so let's even do very concrete things. So let M phi be just 1, 0, 0, 0. Okay, just a very concrete matrix. So can you tell me what is Tn of Grassmannian E M? So the formula says that it should be hom Q n M mod n. So can we compute this guy? So what is this? So it might depend on n, but let's try to understand how. So let me draw the phi. So we have, say, V1, V2, and then W1, W2. And phi maps V1 to W1 and this to 0. Okay. And now we want to compute home spaces from a sub-representation n of dimension 1, 1, 2, M mod n. So how to do this? Home over Q.
We can take some, we have two possibilities for n, right?
Yes.
Okay, then first one is if n is k to k, and if we have quotient by n.
K to k, you mean this is always k to k, but you mean the identity? The
Okay, with identity map.
Yes.
And quotient is k to k, but with 0 map.
Okay. So then what is home?
I think that it's k.
Isn't it k squared, because we can choose both maps as I see. The first one has to be 0.
Right.
And I guess that second case is just the answer is the same, because we have like we have to permute n and m modulo n.
And the second case for n is what?
N is when we have k to k with 0 map,
Mhm.
And quotient is like K to K, but with identity map. And then we have home just of the same spaces, but in different direction.
So K. Oh. And then, so what is M, what N?
K to K with identity map.
But yeah, okay, maybe can you explain why? Is it always true? This is my question.
Well, no, I guess. No, sorry.
This is almost true.
If n is degenerate, it's true.
So you see, there is one special case where it's not true. So because let's choose M, N to be this one and this one. Okay. So this is our N. So just if this is okay, so then indeed this home space is also K. But there is the third option, actually. It's a bit kind of unexpected, but still. So N is 0 and M is 0, mod N. And this is the option. There is only one point of this sort, and the N here is drawn. So N is KV2, KW1. Okay. So in this case, what is the home space?
K squared.
Mhm. Right? And actually, this somehow confirms our picture. So namely, so we have these two P1s. Yes, so this is our Quiver Grassmannian. And then the tangent space to all points here is just a line. But if you consider the special point, then this is a singular point. And therefore, the tangent space should be larger. So there is a direction corresponding one P1 and another P1. Yeah, so this tangent space is two-dimensional. And this actually somehow fine. At least our picture gives such a thing. Okay. So well, I think that's it. That's it for now, and that's it for the course. So do you have any questions, remarks, comments?
So does this singular point somehow give a non-trivial x, or
What do you mean point gives non-trivial x?
so I just didn't. You said something about that when the x1 is 0, then the
Right. So let's, well, I mean, if we consider our M, it looks like just well, like this, yeah. So identity map and zero map, and then x What is X MM? Can we compute it? Andrei, did you say something?
I think that at least for irreducible sub-representations, we know, I mean, no, irreducible components
No, it's not about the
have
components. It's just
X,
about representation itself.
with
What is X MM?
So M is the direct sum of just the indecomposable representation that sends K to K 2 times. So, right?
No. So
it's
you can see
free sub-representation.
there are 3 indecomposables. This one,
The dimension vector was 2, 2, right?
yes, and 3 indecomposable representations.
And the map was the identity map.
No.
Ah, because in this point,
So our M it has rank 1 map. Yes.
because when it doesn't, the next one is 0 and
Yeah.
the 5 is smooth.
Yes. And what is X here?
So we have trivial X from those indecomposable to themselves. So the only non-trivial will be from the K to K to the
No, come on. This is, you should know this. What is X after all? So we have 3 indecomposable summons. So we can compute X between each pairs of summons separately, right?
Yes, we should consider extensions for each pair.
Yes. So are there non-trivial extensions within each pair?
Okay, for one-dimensional cases.
Yeah, one-dimensional too. So the one where we have K on the right, and then the one where we have K to K.
Yeah. So this X is non-trivial, right? So it's one-dimensional, and therefore we don't expect that any Quiver Grassmannian is smooth. Yes, and of the expected dimension of the. So we say that we see that there are some sub Quiver Grassmannians which are not smooth. Oh, this is the key. But I just wanted to say that this algebraic formula for home spaces, it allows you to understand some geometry of the Quiver Grassmannians. So if you compute the home space, you can somehow understand whether the point is singular or non-singular, what are the directions and so on. So some other questions, comments? If not, yeah.
Are the Grassmannians, the universal Grassmannians represented by some functor?
So what do you mean by a function?
So like the classical variety of representations of a quiver is represented by some functor that associates representations of the quiver in the category of locally free sheaves, something like this.
Yeah, there are some constructions of this sort, but they are more complicated. But in principle, yes. In principle, you can somehow mimic the Grassmannian case in the case of Quiver Grassmannians. But but this is well, not the thing one can discuss in a minute.
And do you have some reference or?
Well, I mean, if you can, there are some references on the web page, I think, but there are some lectures by Crowley Bovey, and so you can find there.
And they discuss this or?
So, I mean, there is this quotient construction, which I mentioned in the beginning, and probably this is what you are asking for, if I understand you correctly. So maybe I show you once again. So the construction of this form, yeah. So you can consider this Grassmannian, this Quiver Grassmannian as a quotient of the home spaces of the embeddings by some group. So in this sense, if you're asking about this,
I'm just interested if there's some very specific functor, but
no, I know this construction. Well, but so in some sense, this is the so these points of Grassmannian, they represent the maps from KE to M, but maybe there are some other things, but I don't know. Some further questions?
Well, can you explain about proof of proposition about that if we have rigid space and we have like a constant how to say constant dimension of fiber, right?
Yes, yes. Mhm.
So we have how to say we have that all our base is just one orbit, right?
No.
No. Okay.
We know that there is an orbit which is open and dense,
Ah, right. Yes.
and over this orbit, all the fibers are isomorphic. Yes, because so the
Yes.
representation, and therefore over this orbit, this is just a fibration.
Yes.
But this is the kind of open part of the variety. So the fiber should be of expected dimension.
But it but so then we can conclude that all how to say then all fibers are of also fibers of orbits of small dimension are also of
No.
expected dimension. No? Ah,
No,
okay.
You see, you can see it in this picture. So you have an open part over this open part, the fiber is just P1. Then you go to the smaller part where determinant is 0, but the matrix is non-zero, and then you get two P1s, and over the very special point is P1 times P1 is 2-dimensional.
But here we have X probably, or sorry, I understand.
Depends on the representation. You see whether if you take a point in an open part, you don't have any X. But if you take the point in the the point corresponding to the degenerate matrix, you do have an X.
So you mean that over our base is just representations, and over rigid representations we have yes. Okay, I understand. Thank you. Okay, I have one more question. It's about a bit previous lecture. We had all our construction was kind of from symplectic geometry, like we have reduction, to be honest, and we have cotangent bundle to Grassmannian, which is well known. It is symplectic space manifold, but well, we can try to make something. I know that there is at first there is Poisson structure on Grassmannian, And as well, we can try to obtain Grassmannian by similar procedure if we take framed A1, but we should like throw away J, which is one of the maps. But I need one more detail to make it complete. This is some Poisson structure on I. I mean on space of how to say, on probably on representations, on representation space. So maybe we can consider this example. Just we have like
So you want Poisson structure on the space of homes from one space to another? Or?
yes. Such that after this kind of quotient,
Which I'm not,
we have
not sure. I'm not sure.
okay.
I don't think there is some reasonable Poisson structure in the space.
Okay.
So this is why actually one needs to double the errors. Otherwise, one could do what you suggest, and then would be much simpler. So
Okay.
this procedure of doubling the errors exactly somehow resolves this problem.
Yes, this resolves, but then we have like cotangent
Yeah.
space.
That's right. I don't understand what you mean, but
Okay. Thank you.
welcome. Some further questions? Okay, so if not, I'll upload the last home problem on the web page, and then next time we'll have an exam. Well, I'll send some instructions and the well, we'll just discuss the problems, and the exact time will be distributed a bit later. Okay, so if no further questions, then see you next Tuesday.
Okay. Thank you.
Bye-bye.
Thank you.
Bye-bye.
Goodbye.
Thank you.